In the previous video we have discussed the definition of the external quantum efficiency, or EQE. Furthermore, we have demonstrated how we can compute the short circuit current density from an EQE curve, and we looked at the basic setup to perform the measurement. In this video we will show how the basic setup can be improved, as well as how multi-junction solar cells can be measured by using bias illumination and bias voltage. Finally, we will show a video of a lab scale EQE setup, and we will demonstrate how a measurement is performed. We've shown in the last video that the light source should be calibrated with a reference diode prior to every measurement, since the spectral intensity of the lamp may vary over time. A measurement will typically take a few minutes, which means that any fluctuations of the light source in a shorter period will go unnoticed, making the EQE curve less accurate. This can be solved by switching the probing light between the reference diode and the solar cell for every wavelength step during the measurement. At first, the response of the reference diode is measured, then the probe light is focused on the solar cell on the test, and finally the reference diode is measured again. If the light intensity stays within a tight range, the measured value of the solar cell is recorded. Otherwise, the value is omitted and the same wavelength is measured again. In this way, the error by fluctuating light source intensity can be reduced to a minimum. When we want to measure the external quantum efficiency of a multi-junction solar cell, we need to follow a special approach to obtain the correct response from the cell. A simple representation of a monolithic multi-junction solar cell, in this case a tandem cell, is shown in this diagram by two diodes in series. The top cell will have a wide band gap and absorbs high energetic photons, while the bottom cell will have a smaller band gap and absorbs the lower energetic photons. This can, for instance, be an amorphous silicon and a microcrystalline silicon solar cell, respectively. Typically, it is desired to measure the EQE of the top and bottom cell individually, but in case of a two-terminal solar cell, we can only contact both of the solar cells together. The current will in this case be limited by the cell that collects the fewest electron-hole pairs. When we would measure the top cell with short wavelength monochromatic light, the bottom cell would not absorb any light, and therefore the current produced by the tandem cell would be zero. The solution is to saturate the bottom cell with light that is not absorbed by the top cell, for instance by infrared light. This is called bias illumination. The current of the two cells in series will now be limited by the top cell, which is what we wanted to achieve. The other way around, if we want to measure the response of the bottom cell, we must saturate the top cell with short wavelength light such as blue or ultraviolet. For example, the resulting EQE curve for a so-called micromorph tandem cell that consists of an amorphous silicon top and a microcrystalline silicon bottom cell can look like this. If we would not use any bias illumination, we would only measure the overlapping area between the two cells. Bias illumination can be included in the setup by placing a ring with multiple colored LEDs focused on the solar cell under test. The user can then select short wavelength bias light for measuring the bottom cell's EQE, or long wavelength bias light for measuring the top cell's EQE. There is, however, another complicating factor when measuring the EQE of a multi-junction solar cell. An EQE curve is most commonly measured at short circuit conditions, such that it can be used to calculate the short circuit current density of the cell accurately. Let's take a look at the JV curve for the top amorphous silicon cell of the previously mentioned micromorph tandem cell. We look at the case where we measure the EQE of the bottom cell and apply short wavelength bias illumination to saturate the top cell. The current through the tandem cell will be limited by the bottom cell, since it only absorbs low intensity probing light. The operating point of the top cell will therefore be located close to its open circuit voltage. If we were to apply 0 volts across the entire cell, such that the tandem cell in total would be in short circuit conditions, The top cell would be operated in forward bias, while the bottom cell operates in reverse bias. To compensate for this, we will have to apply a bias voltage such that the bottom cell operates in short circuit conditions when we measure its external quantum efficiency. Bias voltage is also used to examine the electronic properties of the cell, since the collection of charge carriers can be voltage dependent. This is for instance the case for drift-based thin film technologies such as amorphous silicon and microcrystalline silicon. We can see that when a forward bias is applied to the solar cell under test, its EQE curve will have a lower response than when it is measured under short circuit conditions. This is clearly related to the operating point of the solar cell on the JV curve shown here on the left. The actual mechanisms that play a role in the voltage-dependent collection are beyond the scope of this course, but the bias voltage proves to be a powerful tool to detect collection problems. We will now look at a lab-scale EQE measurement setup and demonstrate how a sample is correctly measured. Here we see an overview of the setup, starting with the chopper frequency generator, the light source, the monochromator, a lens system and a bias LED ring, a mounting frame for the sample, a log-in amplifier and the power supply. Before we can take the actual measurement, we will first connect a calibrated silicon reference diode and place it in the probing light beam. This diode will precisely measure the photon flux of the light source at each wavelength step. The light spot is green before the measurement for good visibility. During the measurement, the monochromator will select the wavelength in desired steps, starting with UV light all the way up to the deep infrared. Halfway, a grating in the monochromator will be switched, now using one that is optimized for longer wavelengths. When the calibration is finished, the spectral photon flux of the light source is saved in a data file. We can continue by carefully placing the solar cell under test in the mounting frame. This mounting frame is isolated such that no current can leave the cell unnoticed. Contact probes with gold tips are placed on the back contact and on a bus bar at the front side of the cell. The light spot is then placed at the middle of the cell where no contacts are present to avoid shading losses. When taking the measurement, the EQE curve will directly appear on the screen. Please notice that this part of the video is played in fast forward. On the left-hand side of the screen, we can define the wavelength range and step size of the measurement. In advanced options, also a range of bias voltages can be defined. The external quantum efficiency of this particular solar cell is above 95% in the mid-range wavelengths. However, there are inevitable reflection and collection losses in the short and long wavelengths, respectively. High-intensity white bias illumination can be applied to simulate operation under one-sun illumination, as was mentioned in the previous video. The bias LED ring further contains the colors ultraviolet, cyan, blue, green, red, deep red and infrared. To summarize this video, we have shown how the influence of instabilities of the light source can be minimized by alternately measuring the reference diode and the solar cell. Furthermore, we have demonstrated how the EQE of a multi-junction solar cell can be determined by using various colors of bias LEDs and voltage bias. Finally, we have discussed that bias voltage can also be used to determine electronic losses in a solar cell.